Recording. All right. All right, guys. I'm Özgün Akteğmen, one of the research assistant in under the Department of Civil Engineering of Antalya Bilim University. So, last 6 to 7 years, I'm working on hydrological models, and I'm here to share some specific of the projects and give you some information about hydrological models. All right. So usually this is what's happening, right? In the nature. So precipitation happens in various kind of ways. After that, some of the water infiltrates inside of the soil. Some of them goes for runoff, and it is called excess precipitation, right? That surface runoff meets with the oceans, seas, then it evaporates from the surface and evaporates from the plants, and both they are called evapotranspiration. Then it condenses again, and rain or snow or any kind of precipitation to the surface again. So this occurrence is called generally hydrological cycle. So let's go for the next slide. Now, the thing that we are looking at called is watershed. So this is our basin, and that red lines indication of the watershed, which is corresponding to highest elevation points of the basin. So every water droplets or every kind of precipitation that is dropping inside of this region will be inside of the water budget of this basin. So our studies are working in that kind of watersheds all the way. So what is simulation? Why we need them? Why are we doing this? Because in real life, these basins are really large, like 7,000 to 10,000 kilometer square areas we are talking about. So we have plenty of different data. Data also changes according to location, as well as they change according to the time. So the kind of data that changes according to the position that we are looking at is called spatial data. And the data that depends on the time is called as time series data. So basically, these are our inputs for the models. And the reason that we are creating models, since these areas are really huge, so it is impossible for us to understand in real life how this is happening. So we have to have some concepts, and simulations are giving us really good insight of what is really happening in that region, and we can check our results with the gathered real-time data. All right, these are the general informations of the hydrological models. These are the components. Hydrological models are built one layer at top of each other layer. So first we have geomorphologic data. Basically, we are using digital elevation models for this sense. We have land use data. There's difference. There's lots of different classifications for the land use data. For example, one land can indicate some agricultural field, and other land can indicate some urban settlements. So these informations are important for us. Also, we have soil informations. What kind of soil texture that area have? What is the silt content? What is the clay or sand content? How much? What is the depth of the soil? These are all of them are important data, and the first three of them that I just talked, these are spatial data. Basically, they change according to the locations. But the third one, meteorological data, is time series data. So they change according to time, according to the date. It differs according to your resolution of the data. How much, for example, 1 hour data, so, or 1 year data. Basically, it boils up to what is your aim? Well, what are you aiming at in order to build the model? Let's say we are trying to see effect of a flood, effect of a precipitation, excessive precipitation in a region. Will that cause a flood or not? If you are looking at this situation, the resolution of data should be really small, like at least 1 hour resolution meteorological data we are looking at. Because let's say 150 millimeter of precipitation occurred in just 10 minutes is a disaster. You will see a flood. But if that is precipitating in 1 day, nothing happens. So the density of the resolution of the data is very important. Okay, let's see. This is the hydrological model flow diagram. You are seeing that the precipitation first facing with the vegetation. After that, the vegetation usually we use as a buffer zone. It delays the amount of water to be go into the land. After that, the part that is not accessing the infiltration capacity goes for infiltration, but the amount that is overtapping the infiltration capacity will go for the surface flow. All right. The next slide, there's lots of different methods, and I will not go into deep all of them because it will take lots of times, but this is one of the most famous one, SES curve number method. We are using this method in the usually for the flood analysis, and it is invented by the United States Department of Agriculture. There's different infiltration methods I mentioned, and probably you saw them on the lectures also. This is Horton infiltration method. Basically, if you know the maximum infiltration rate when the soil is bone dry, and you will face with the saturated infiltration rate, the lowest one when the water is saturated with water. Another method is green and empty method. It requires lots of parameter. As I mentioned to you before, it boils down to what kind of parameter you can put your hands on. So you have to shape your methodology according to the data that you can achieve. For example, this one is a soil moisture accounting, and also this is called as a bucket type model. Why it's called a bucket type model, you can understand from this flow diagram. So every parameter of the soil, canopy storage, surface storage, upper and lower storage, groundwater storage, these are modeled as a bucket. So the relation between each layer gives you the model itself. And we have evapotranspiration methods. This is one of the most famous one, Thornton-White method. We have Blenny-Criddle method. We are using this one usually on the design of the agricultural structures, the irrigation infrastructure. And this is one of the rarer one. Recently, I'm using this one, Hammond method. And we have now we are going for the surface flow methods, unit hydrograph methods. Kinematic wave method, you can use it if you are willing to add a subcomponent, hydraulic subcomponent, hydraulic model you can implement inside of your hydrological model. And if you are asking how it looks like, the programs that we are using, one of them is GWLFE model. Currently, this is the one that I'm using in the project recently I joined. So as you can see, this is our sub-basin, and we have lots of little catchment areas. So it is a density also. So if you are willing to use more smaller catchment areas, your model will be more detailed and more tuned for excessive flood event, more tuned for the more intense precipitation events. And in the end, we are trying to achieve this. Now, the predictions shows these orange lines. So let me show you like this. Our control basin in here was here, just at the end of the sub-basin 10. So it is located at the northern eastern side of the basin. So in that basin, we are looking for the flow observation station. The data coming from the flow observation station given in the blue dashed line. And our predictions, our model's predictions, is the orange lines. So in some sense, they are matching, right? But not exactly. So the accuracy of your model is measured like this. We have different indicators or coefficients in order to measure how accurate the model is. For example, the Nashville sufficient and R square. These are all these indicators. And maybe the most important thing is why we are doing this. So you have to ask this question to yourself: why we are just modeling or designing that kind of models? The reason is, you are all civil engineering students. If you are working in a structure, just imagine you are designing a building. You have to simulate the performance of the structure with some load, and that load will be corresponding to it can be earthquake load, it can be dead loads, it can be even the humans inside of the building. These are all the loads. So you are just checking your structure if it can be withstanding according to these loads. And if you are building a hydraulic structure, it can be a dam, it can be an irrigation system, or it can be a weir. Your design load will be coming from hydrology. So this is very important. Of course, the structure should be standing there under the earthquake conditions, but also your structure should be supporting, giving your structure should be acting as it intended under the hydrological conditions. So we are finding the hydraulic loads from the hydrology. Now I will give you a couple of informations from the projects that we worked together with Ali Hoca. One of them was the Gazi Pasha flood analysis. This was a study located in the Gazi Pasha region. We try to analyze the field, and because why we are analyzing, because this field is important with the excessive precipitation happened. Also, the flood events are seen in this region. So we try to see what may be the results. In here, we compare 2 years. One of them is 2013, and another one is 2019. What will be the human activity, or does the human activity is the result of these floods? In order to see that, we built this model. This is another one, which is Karakuyu Basin. Karakuyu Basin located some northern side of Izmir, and under this basin, in the past, it was in 2019, I think, the company was asking, there's a water accumulation over the surface, and we want to know how much water accumulation happening annually. So they were planning to use this water in order to supply and build an underground dam, and they wanted to know what is the potential. In order to do that, I created a hydrological basin model for this region, and I think, if I'm not mistaken, annually it was 8 million cubic meters of water is accumulating over the surface. This is another project that I work in. It is a drainage infrastructure design. In the end, you should be doing drainage infrastructure, but before starting to design your infrastructure, you should be knowing that how much water will be coming from each region. So in order to do that, I use a couple of informations. First, I draw all the buildings inside of the area, because these building areas are the representation of impervious areas, and all the water is touching to impervious areas will be going for the surface flow. So this is something important. And after that, these areas are showing you the surface slopes. If your surface slope is high, the surface storage will be lower. So water will go outflow, not it will not stand still too much on the surface. If it is a steep slope, water will be go outflow really fast in a precipitation event. And the left side is showing impervious areas. As you can tell, the more darkish colors are indication of more impervious areas are happening in here. So we are expecting more water to come from that region. In the end, we are going for a design after using this information. Now the hydrological part finished, and we are going for the design of the structures. All right, this is a project started from 2016 to 2019, I think. It is a TÜBİTAK funded project. For this area, we designed 2 hydrological models utilizing 2 different methods. One of them was the SCS curve number method that I previously showed at the upper side, and at the lower side, we use soil moisture accounting, the bucket type model, to simulate what will be the groundwater percolation rates in this region. This is important for the agricultural purposes. And the next slide is Doğançay Cemetery area. At the left side, you are seeing a digital elevation model. At the lower left corner, you are seeing our cemetery area. Basically, municipality asked us to show us if there is a flood problem in this region, and also there is no drainage infrastructure established in the field. So please give us a drainage infrastructure for the area. And at the right side, you are seeing our analyze in here. It is called as, the program is called as HEC-RAS, one-dimensional flood analyze. So in here, we checked the basin, and there wasn't any flood problem for the region, but from the excessive precipitation in the region, there is flow accumulations over the land. So, and these water eventually goes for outflow on the roads because there's no drainage infrastructure. In order to fix the problem, we designed a drainage infrastructure for the field. All right, this is another project, one of the most oldest one, I think, that I've worked in. Yamanlar project. Instead of one-dimensional flood analyze, in here we use two-dimensional flood analyze. As you can see, there is lots of meshes you are seeing in the region. So this is again the HEC-RAS program, but it is working on the two-dimensional field now. When we apply the precipitation, then we saw this kind of water accumulations, and water will be going outflow from the field. Basically, why we did this is the municipality asked us if we locate the waste disposal site in this region, will it be affected from the floods? Because of that, we try to achieve a hydraulic model and find the result. So to wrap up, as I told you before, this is something important. If you are designing a hydraulic structure, the loads are coming from hydrology. So this is something really essential, and by this way, I'm earning my life, and maybe someday you will do the same thing. Thank you. Thank you for your attention.
Thank you so much, Özgün.
Okay, maybe I can have some questions if you have.
Any question from students? No. No question. Okay, Özgün, you talked about Gazi Pasha project, but you can you go back to that slide, and if you have, go back to Gazi Pasha project. Yeah, if you have access to our paper or the flood, that we have some figures about floods and the result of our study.
I can find it easily, I think, from the school's website.
Yeah, and show the results and a bit more discussion about the results and what kind of solutions. I can also talk about that figure for the students, maybe.
Okay, hocam, now I'm bringing that up. It may take some time, just 2 minutes.
You just open the paper, maybe from Google Scholar page. Go to internet and share your Google Scholar
page. I can try that too. All right, now I'm sharing a tab with you instead of this one.
Thank you.
Can you see it now, Professor?
Yeah. Good. Open the PDF file and let's see the flooding figure. Yeah, this is a study area, and this is the location of the. You see, students, that it was maybe 2019. Yes, if I'm not 2021. Very recent.
21.
Yeah, very recent. Intense rainfall event happened in Ghazi Pasha, and by wrong decision of one of, maybe it was task office, yes, vergi dairesi, task office. The task office is somewhere around the corner of this square, and they made their archive on the underground floor, and after this event, they reported that most of the archive, most of the paper documents that they have in tax office was get wet, and maybe they don't have access to those papers, and this is it shows several mistakes that that can be done by managing. First, location of the, for example, in terms of that department, location of archive should not be the underground floor. However, I just mentioned that issue because it was very interesting news in that time for me. Then we started to do analysis with Özgün to check what happens there and why we have such flooding issue in this region. And we understood that the main reason is urbanization, fast urbanization. And yeah, here Özgün shows you the land use land cover map of the city. LULC is land use land cover of the city in 2013 and 2019. And we our analysis showed that during the past 7 years, how many percent we had increasing in urban area? Maybe
80% increase in impermeable areas.
Yeah, look, 80%. What does it mean? When you increase urban area or impermeable area 80%, there is no infiltration and there is no loss, there is no pounding the water detention in natural ground. So what comes as a rainfall or precipitation on the ground transformed directly to the runoff, and this is the current situation. You saw the flooding. Therefore, in order to avoid such problems in the future, what we should do? This is my question from the students. What we can do to avoid such problems in the future of this city? Definitely we will have the same rainfall and in the future, and definitely if we do not do anything, we will see such problem, flooding and inundation of buildings, streets. Again, do you have any idea? Can you guess any kind of solution for this problem? Zaid, you want to talk?
Good afternoon, teacher. Yeah, actually, I think we should work better on the drainage system of the roads.
Good, great idea, Any other idea? Okay, so yeah, redesign of drainage system consistent with the new condition. In brief, when we increase urbanized area, when we develop impervious or impermeable area, therefore definitely we have higher runoff, and therefore we either we should we should increase capacity of our irrigation system, our drainage system or sewers, or we should do something at upstream from the places that runoff collected and comes to those hot spots, to those locations that we see flood in that locations. And some of the methods that we can control such amount of runoff could be working at upstream by installing small check dams, maybe by increasing green area, and by some other works that there are so many works, but any city has its own condition, and a civil engineer who is a specialist in hydrology should think about potential solutions for such problem and suggest some ideas. In general, any municipality needs some hydrologists, hydraulic engineer who are expert in these topics. And this is one field that you can increase your knowledge in hydrology to improve living condition in your city. Okay, thank you again, dear Özgün, for your nice lecture and experiences that showed how a civil engineer can work in the field of hydrology. If you have extra things to share with the students, please go ahead, and then we can finalize or end this session.
Hocam, thank you for giving the opportunity to talk with you. Thank you again. See you next time.
Okay, thank you. Have a good day. See you. Bye-bye.